In the last video, we built a single leaky integrate and fire neuron. But a brain doesn't contain one neuron. It contains a network of neurons communicating with each other. So today, we are going to take a single neuron, gradually turn it into a spiking neural network. And by the end, you'll see how an individual spike can propagate through an entire network. Before we build the network, let's quickly look at the framework we're using, Brian 2. Brian 2 is an open source Python-based simulator designed specifically for spiking neural networks. One of the things I like about Brian 2 is that the code maps quite naturally onto the concept we are trying to model. We can easily define neurons, synapses, and networks using mathematical equations written almost exactly as you will see in the paper. Instead of forcing you to fix set of predefined neuron models, you can define your own custom neuron model, your own custom differential equation explaining neuron dynamics and synaptic plasticity. Another thing about Brian 2 is it has built-in systems for physical units. This helps in avoiding common bugs from mismatched units, keep your model physically meaningful, and make your code more readable and reproducible. Let's start with a brief recap. We defined leaky, integrate, and fire neuron. We factored three important things: incoming current, leakage toward the resting potential, and generation of a spike when membrane potential reaches threshold. These were some parameters we defined: time constant, resting potential, threshold, what happens after we cross the threshold, and resistance. This is how we defined our model, how membrane potential changed over time, our leak factor, resting potential minus membrane potential, our input factor, resistance versus multiplied by current, our time constant, and notice the units. How did we create one neuron? We used something called NeuronGroup. We created one neuron. We defined our model. We defined our thresholds. What happens after we cross thresholds? Something called refractory period, and what approximation method we use. Then we defined our initial condition. Membrane potential starts with V underscore rest. Our constant input, in this case, 0.2 nanoampere. We set up our state monitor and spike monitor to monitor potential and spikes. This is how we run the simulation. Then we plot our membrane potential. To first do this, we have to import NumPy, matplotlib, and Brian2. NumPy for numerical operations, matplotlib for visualization, plotting, Brian2 for spiking neural network simulation. We define small chunk of time, dt. Here we have 0.1 millisecond. We define our parameters. We define our model. We create one neuron, our initial condition. We set our monitors. And finally, we run the simulation. Now let's see the plots. We can see the membrane potential. We start from minus 65 millivolts, rise slowly, touch threshold, drops. Back to minus 65 millivolts and start again. Now let's talk about time constant. You can see this thing reaches threshold in about maybe 18 milliseconds. So let's change that. Let's change our time constant to 20 milliseconds. Our equation is already defined. Let's just do it again. Set our initial condition. and run. Keep this in mind, especially 18 milliseconds. Now notice this huge time. So that is how time constant affects our model. It takes a lot longer to reach this threshold if I increase the time constant. Another thing I wanted to talk about was refractory period. Refractory period is the time neuron needs to recover from a spike. So for example, when our memory potential reaches threshold, it is dropped back to resting potential, and then neuron rest for refractory period of time. So for that period, neuron cannot do anything. It will take a break, and after that refractory period, the memory potential will start rising again. So let me show you how that works. You defined a refractory period here, and there was another term in our model, unless refractory. I have commented this out. So I remove the comments. Now we have our model with this thing here. So let's increase that to say 5 milliseconds. That is the amount of time neuron needs to recover. Let's again set this to initial stuff. Let's set our monitors. Let's run the simulation. Great. And let's run the plot. Notice this. This is the time neuron needs to recover because of this 5 milliseconds refractory period. Now let's create more than one neuron. I want to reset my original parameters. So set this back to 10 milliseconds. Run it. This one. Okay. So a biological neural circuit contains population of neurons rather than a single isolated neuron. In Brain 2, we'll use NeuronGroup, which allows us to create multiple neurons using the same neuron model. So we used this last time. We had one here for one neuron. Now we're putting 10 neurons here. Everything else remains the same. Run that. Sorry, I did not define the model. Here it is. It seems to be defined, but I don't know. Okay, so we have defined our model. So let's try again. It worked. 10 neurons. Everyone gets the same input. State monitor, our spike monitor. Put them in some sort of network. So this network will observe all these neurons, will get all the memory potential, and everyone spikes. Let's run this. So this time we are monitoring only spikes. Last time we monitored membrane potential. So let's see how that goes. Great. So on the vertical axis, you see neuron number. So this is the 0th neuron, 1 neuron, 2 neuron, all the way to 9 neurons. So we have 10 neurons starting from 0 to 9. These dots represent spikes. So the first spike happened around maybe 14 millisecond time mark. Then the next one maybe around 29 millisecond time mark. Everyone is spiking at the same time because they have same constant input. This is for mathematical understanding. We have resting potential. I believe that's minus 65 millivolts. We have 100 mega ohms resistance and 0.2 nanoampere current. So we get 20 millivolts, and we add 20 millivolts to minus 65 millivolts, we get 45 millivolts. Since 45 millivolts is greater than minus 50 millivolts, every single neuron is spiking constantly. Another question you may have is this time gap. We start from nearly 15 milliseconds to 30 milliseconds, and from 30 milliseconds to nearly 45 milliseconds. Every time, there seems to be a gap of approximately 15 milliseconds. Where did 15 milliseconds come from? To understand this, we start from our original leaky integrate and fire equation. Okay, so this was our equation. We open this up. We define equilibrium value, we resting plus our input. We arrange our equation according to like this. We move our time constant to this side. Now notice this interesting equation here. If this thing inside the bracket, our memory potential minus our equilibrium potential, is small, so the difference here is small. If this thing is small, this change will be small as well. If there's a huge gap, if we have v minus v infinity is huge, this number is huge, then this dv by dt would be huge. So this thing states that the rate at which memory potential changes depends on how far memory potential is from equilibrium value. If this is very near it, small change. If it's very far from this, a huge change. Then we carry on. We move all the v term on one side and the rest of the term on the other side. So we have something like this. Then we have to get rid of dv and dt. We do this by integrating. Since this is on the lower side, this is standard integral formula for this. So you get natural log. So we have natural log v minus v infinity and this t. To remove natural log, we add exponential. So we have exponential on both sides. We get this here and this one here. Exponential by c, it's a constant. We can write it like this. So we have this as our equation. We also know that we start from our resting potential, right? So if we start from our resting potential, this time will also become 0, and this will be 0, right? So this becomes 1. So v infinity plus constant. So this is where this comes from. So now we have what the value of constant. This is the value of constant, and this is our final equation here. So I hope you understand how we got this equation. Now all we need to do is put some values in there. So we have this. We calculate this to be around 45 millivolts, and this is our resting potential. So we have 65 millivolts. We already know the threshold, which is 50 millivolts. So this equation comes here from this thing. 45. This one. This thing's here. Our time constant is 10. This gives us approximately 13.86 milliseconds. We also have 2 millisecond refractory period, I believe. So that will give us approximately 15.86 milliseconds. That is where the gap is coming from. You don't need to understand the math 100%, but just have a general idea how and where this time is coming from. And so now we have 10 neurons, but there's a problem. These neurons aren't talking to each other. They're independent, all of them getting constant input, and all of them spiking independent of each other. Let's start our next part, how to get two neurons to communicate. For this, we use something called synapses. Basically, it works like this. You have our first neuron. It reaches the threshold. It emits a spike. This spike crosses synapses, the connection between another neuron. N2, the second neuron, receives the synaptic input because of this synapses. Its memory potential changes, and eventually, in our second neuron, spike. So basically, we have a presynaptic neuron, a postsynaptic neuron. The spikes travel through synapses. How do we do that? Well, We again create a neuron group, this time with 2 neurons, and everything else, as you can see, is same, no problem. So now we have 2 neurons. We have N1 or N2, 2 neurons. So our constant input will be 0. Both of the neurons are getting 0 nanoampere, right? So no input. But then I change this for our zeroth index. So the first neuron, N1, get 0.2 nanoampere input. Our second neuron does not. So N1 get external current, N2 receives nothing. Therefore, N1 can fire, but N2 cannot spontaneously fire. If N2 later fires, we can attribute that activity to synaptic conditions because there is no input for N2. To do this, we have to define synapse. This is a weight of our synaptic connection. So how does it work? We define synapses using this module here. So it connects this neuron with this neuron. There's the same group. That's why I have to rewrite them, but we could have different neuron groups as well. Source is neuron, target is also neuron on presynaptic here. So this thing means whenever presynaptic neuron generate a spike, add W to postsynaptic neuron input current. So how do we connect it? We connect our 0 ones and the J ones. So this one is source, one is destination, and we define the weight, which is defined inside the Synaptic module with the W we defined here. And then we do the same thing. We create a network, we have state monitors and everything, and we run it. So let's check it out. Connection, monitors, our network. Let's run this simulation. So just telling us which W it's using. Hopefully nothing wrong. So finally we plot. What are we plotting? Again, we are plotting only spikes at this moment. You can see on the bottom are the spikes from our first neuron, and on the top the spike from our second neuron. The first neuron is getting constant input. Here, our second neuron is not getting any input from anywhere else. The only source of input it gets is from this one. Whenever the presynaptic neuron generates a spike, add 0.1 nanoampere to postsynaptic neuron input. In our case, W. So this is how we are getting these spikes. We can check our memory potential as well. Notice something interesting. So this blue one is from our first neuron. This is memory potential of our first neuron. The orange one is memory potential from the second neuron. The dotted line is the threshold. So notice it's completely zero. This thing is rising because of constant input. The moment it spikes, something happened here. We have a rise. Some sort of input is coming into our second neuron. Then we have this refractory period. It goes up, up, here, all the way here. And then we have another spike, another, we start right. Going up, all the way here. Another spike, up. Finally, we have thresholds. We go down, again, we have this refractory period, and we move up again. So, what will happen? When neuron 1 fires, The spike doesn't magically appear in neuron 2. The synapse convert the presynaptic spike into input to postsynaptic neuron, causing its membrane potential to change. You're seeing this rise here. So let's do some experiment, right? Let's change our weight. This weight is defining how much input or how much effect the neuron 1 is having on neuron 2. So let's change that and see how we can, what effects we will have here. So for this experiment, I have created this large function. This one basically creates a neuron group, the two neuron group we had. We set all the initial values in the same way we had before. We define the synapses as we did before. Same connection, not to rate. Synaptic rate, I believe, coming from outside the parameter. Yep, parameter. This is what we're going to change. We define state monitor and spike monitor in this function, define the network, and return all that. We have another function that plot both, I think, yep, there's a membrane potential and the raster plot. The raster plot would have spikes. Spikes. So let's see what happened when I change these weights. So define this function, define the plotting function. So here I have two values here. I think this is same. This portion and this portion, I believe, same. Only thing is different is the weight, the synaptic weight, right? So this is very weak. Let's see what happens. So membrane potential of neuron 1 is rising, and slowly, and 2 membrane potential is rising, but it never reaches the spike. So we only see spikes of first neuron, the second neuron never spikes. So again, I did not change anything, only the weight. Let's increase that weight to this one. I believe we already did this one. So this is the graph I think we saw last time. So spikes, and after this spike. So this entire change is happening only because of this weight change, nothing else. Neuron 1 is same, neuron 2 is same, the constant input is same, everything is same. Only thing that changed is the weight. There seems to be a issue. Look, the leaky integrated fire model was very clear that once the neuron fire, it is reset. It goes back to its equilibrium point, right? So we can see that here. The blue line goes up, hit this dotted line, goes back, that's the threshold, it's reset. So same way, this orange line is raising up again and again. The moment it hits the threshold, it goes back down. Everything's fine. After refractory period, what happens? It jumps back. You can see this here as well. It took nearly more than 60 milliseconds for the first spike, but the next spike happened in much shorter time, and it seems to be reducing. I don't know if I can simulate this better. Let's see if I can. Strong rate, so let's increase that number to say 8. I don't know if it works or not. Let's see. You can see the frequency seems to be increasing. So how does that work? I mean, wasn't it supposed to reset? the gap is decreasing. N2 firing is more and more frequently. If N2 is resetting after every spike, why is its firing frequency increasing? So the problem is there are two separate things. We have membrane potential, so that is being reset. You can see it here. The moment it hits the spike, it goes back to resting potential. I think that is 65 millivolts. But synaptic current, we're not changing that. The original rule in this function, we look at the function, whenever there's a spike from first neuron, add, I believe, 0.1 ampere to that second synaptic current, right? That was the rule, that every time there's a spike, our second neuron current increases by a certain step. We are resetting that. That value, it remains the same. So that is why the frequency is increasing, because we are never resetting this thing. So this is our original equation. As I gets larger, or mi, the input term, gets larger, therefore membrane potential rises faster. The increase in frequency of firing of N2. Small I, slow voltage rise, longer time to threshold. Large I, faster voltage rise, higher firing frequency. The amount added to the postsynaptic current is controlled by synaptic weight, W. We wrote this equation last time. Whenever the pre-neuron spikes, the postsynaptic neuron has some unit added to it along with its weight. So when you have a small weight, you have a small rise, a large weight, a larger effect, right? But the problem is, it's very unrealistic. It is never reducing, never decaying, never resetting. So we're going to add a small gradual decay, an exponential decay, if you will. This is the new term, new equation we will add. S represents current contribution produced by synapse. ds by dt, how quickly is synaptic current changing with time? ds by dt minus s divided by a time constant for this particular variable s. Again, if you move this to this side and dt to this side, so s terms on one side, the other terms on the other side, you will again have 1 by s d of s, which, if you remember, when we integrated it, we got natural log. To remove natural log, we have exponential. So this is basically an exponential decaying form. Our new equation would look something like this. Instead of using I post, I will use F to represent the current contribution. Every time there will be a W factor added to F, and as this time goes by, we will have some factor of S decaying naturally. We'll add this in our synapses portion. This is how it was before. We added this little thing here. This will have S decaying naturally, and everything else remains the same. This is the new function. We're still only taking the weight. This is the time constant for which tell us how long it will take for the current contribution to decay. Our original equation, but we added this little thing here. The neuron group is same. This thing now defines we reset our resistance and our time constant. Initial conditions. So this one, external current, no, no synaptic current either, and only one neuron is getting some input. The synapses I just defined for you on pre. W will be added to S every time. This is the time constant for synapses decay. Same way, same way, same way monitors are added. Instead, we are also monitoring this now. Okay, let's run this. And notice unless refractory has been removed. So the difference between these two is just the weight. And let's try the weaker one. So the blue one shows the membrane potential of the first neuron. It spikes here, and due to this spike, we can see the membrane potential of neuron 2 rising. After this point, it starts decaying. After the spike, again neuron 2 rises. Not quite the threshold, decays. The next spike causes second neuron to spike. Reset, and then again slowly rising in half. As you can see, this decays. What if I increase the weight? So now you have more spikes. You can see a small gradual decline here because the S factor is exponentially decaying. So you have this portion, this decaying portion here. The next time decaying portion a little bit lower, next time a little bit lower, next time a little bit lower. So every time it will require more from neuron 1 to spike. Now let's move on to our last experiment. We will create a 10 neuron chain. So we will have neuron 1, which will have an input, which will spike to neuron 2, which will contribute to neuron 3, all the way to neuron 10. For simplicity, we will not add this decaying factor we added last time, and we will use our old simple one. So this one defines our chain. So basically, we have 10 neurons, we have some synaptic weight, these are our parameters. So we get 10 neuron model. We go back to the simpler form, our initial condition. Everyone gets zero input except our first neuron. The same way we created synapses before. This is how we are creating connection between 10 neurons. And this is same. Okay, so let's see what happens. So this one starts with 0.5. We didn't define our model. Our model. Let's use our original model. So let's try again. Yep. Everything ran, no problem. We have this new way of plotting here. Again, we'll be plotting the spikes and all 10 of our spikes. So basically, again, the neurons are on the vertical axis. The first neuron all the way to 10 neuron. This is constantly spiking because of constant input. Then our second neuron takes these many spikes from our first neuron to spike. And then again, you notice the increase in frequency because there is no decaying S factor. About after three spikes from neuron 2, our neuron 3 starts spiking, again the frequency increase. Then our fourth neuron, fifth neuron, and sixth neuron. So basically, you can see the wave propagating from the first neuron to the, I think, sixth neuron. You can increase the weight here. Let's say we increase the weight to, let's make it on, larger effect. And let's see what happens. Yeah. So now all the neurons are spiking. All over here. This one is the only one that's getting the input, and everyone else is, and the spike is propagating along the chain. So in this video, we started with individual leaky integrate fire neuron. We created a population of neurons, connected the two neurons with synapses, explored how synaptic rate affects their interaction, looked at some synaptic dynamics, and finally connected multiple neurons into a network. We've also watched spike propagate through network. But there's a problem. So far, we have chosen the synaptic rate ourselves. Biological neural networks don't have somebody manually setting every synaptic rate. In the next video, we'll ask much more interesting question. Can a network learn those rates from spike timing or some other way? That's where STDP comes in.